Okay, dear students, let's start from where we left in the last lecture. Actually, my phone is not working properly, so it's becoming a little difficult to record things. Okay, so this course is MTH 604 and also MTC 204. The differential geometry, the basic differential geometry, elementary differential geometry that this course constitutes. Now we so far have defined a curve alpha, a parameterized curve to be more precise, as a function from I to Rn that is differentiable. By differentiability we mean that its components if alpha of t would have components like x1t up to xnt, the derivative of all of these component functions exist. And since we are taking our n to be 2 or 3, therefore alpha at t we denote as either x at t, y at t, z at t in case of 3 dimensions, and in case there are just 2 components, it's just 2-dimensional curve, a plane curve, then we just have x at t and y at t. And of course d alpha by dt, which we denoted by alpha dot vector, is nothing but the component-wise differentiation of the curve. Okay, then we showed that we could parameterize the same curve in more than one ways, but that basically just changes the speed or the orientation of the curve, because when I define a parameterized curve, it automatically gives it a direction. Okay, now last time we also defined what is a regular curve. Regular curve is such that norm of alpha of t is never 0 for any t. All its points are regular. That would be a regular curve. Then we also defined what is a unit speed curve. Now unit speed curve is what? Unit speed curve is a curve whose velocity vector alpha dot t is equal to 1 for all t. Like if I take the parameterization of the circle, so you had alpha at t is equal to cos t sine t. This is a unit speed curve. But another parameterization, if I take cos of t equal to cos of 2t, it's again another parameterization of the same curve. The unit circle is circle with center at origin and radius 1. Now this is not unit speed, you can easily check. Although they define the same curves, these are two different parameterizations, and one of them is unit speed curve. Now the theorem that we are going to prove would be that a curve is regular if and only if it has a unit speed reparameterization. So the statement of the curve is, the statement of the theorem is, okay. The statement of the theorem is a curve has a unit speed reparameterization, and if we can reparameterize it such that its velocity vector is of magnitude 1 for all values of the parameter t. Reparameterization if and only if it is regular, if its first derivative does not vanish anywhere. Okay, for to prove this theorem we need a couple of lemmas. Lemma 1 is that any reparameterization of a regular curve is regular. If a curve is regular, no matter how we reparameterize it, it will continue to be regular. And regular, I mean its derivative, the modulus, its derivative does not vanish anywhere. Any reparameterization of a regular curve is regular. Now, since you will consult your study material, this lemma is very, very easy. It can be easily proved. So then we have to prove another lemma before proving the theorem, and that I'm going to do here. Lemma 2. Lemma 2 is if alpha t is a regular curve, is a regular curve, its arc length that we have also defined earlier, S at any point t is a smooth function of t. Now we are going to prove this here. Now remember that arc length at a point t is obviously defined from a suitable point t naught to t, and the definition is you just integrate the speed or the magnitude of the velocity vector. As I have said that we can always visualize a curve as the path traced by a point in case in n dimensions, or let's do it as it is in our case in 3 dimensions. This is a moving point which describes a curve. Then we can, if alpha t is the curve, then of course alpha dash t would be the velocity of that particle. Okay, now this is the definition. Now we want to show that it is smooth, right? Now first thing is straightforward, and also let's talk about smooth. Smooth means it is differentiable. Now if I differentiate it with respect to t, it is clearly alpha by the fundamental theorem of calculus. This is what ds by dt is. It very much exists. Why? Because okay, it very much exists. The function ds by dt is differentiable, but as I said, no, I didn't say it earlier, that smoothness is context dependent. In our case, smoothness means it actually जो s है, the arc length, it can be differentiated. It's differentiable infinitely with respect to the parameter t. So firstly, if I differentiate it first, that is obviously magnitude of the velocity vector, and that is in fact non-zero, because if the curve is regular then it would be non-zero. Furthermore, it is just it is the magnitude of some scalar. Okay, it would be if I have alpha dot at t, sorry, it should be alpha dot t. Oh, because I have differentiated. So alpha dot t would be nothing but you just have its components, no matter how many components. Suppose it was a curve in 3-dimensional space, then it would be just x dot t square plus y dot t square plus z dot t square. And if the curve is regular, then each of these components is non-zero. So derivative not only exists, it is non-zero. In fact, it is positive because it's magnitude of a non-zero vector. So that way it is differentiable and it is smooth. Not only that, we will prove that it can be differentiated more than once. We can just it's more than smoothness, as I said, is context dependent, and in the case of differential geometry we usually require our functions to be at least twice differentiable. The reason being that because what we are going to define as a curvature of a curve would be basically, we can get that only by differentiating our function, our curve alpha twice. So okay, now the proof would be, we just prove it for a plane curve, and our function, let alpha be a function from an interval to R2, and let's call this interval AB. It's all given in your study material, so read that carefully. So that alpha at t would be some differentiable functions ut, vt. It will have two components which themselves would be, what is u? U is just a differentiable function from r to r, and v is also a differentiable function from r to r. Now, they are normal scalar functions that you are used to. And okay, now let's take f, which is a function from r2 to r, defined as f of uv is equal to square root of u square plus v square. Then ds by dt, which is basically norm of alpha dot t, it would be square root of u dot square plus v dot square, which is basically f of u dot comma v dot, as per our definition. The same argument would apply to an n-dimensional, 3-dimensional, 10-dimensional curve. So there is no issue. Okay, now clearly, if I want to find this this function, if I look at this function f from R2 to R. Now, now it's a function of two variables, not just a single variables. Now, the smoothness for a function of more than one variables, it's about the existence and continuity of its partial derivatives. So if I take the partial derivative of f, now del f by del u, as you can easily evaluate, is u divided by root of u square plus v square, and del f by del v, the partial of f with respect to v, would be this thing, right? Now both of these partial derivatives are well defined as long as uv is not equal to 0, 0, right? So that means if they exist and are continuous except at 0, 0, so that means f of u dot, so that means f of u dot v dot, which is this thing, would be, is smooth, is differentiable further. That means s is differentiable further because it is ds by dt, is a smooth function provided u dot v dot is not equal to 0, 0. So therefore, if the curve is regular, it by definition means that u dot v dot is not equal to 0, because alpha dot t is not equal to 0 means if and only if u dot t is not equal to 0, v dot t is not equal to 0 simultaneously. And it's not a zero vector. So it's not a zero vector, and if it's not a zero vector, we see that del f by del u and del f by del v are well defined and continuous because it's quotient of two continuous functions. So that means ds by dt is a smooth function. So ds by dt is a smooth function. Of course, s is itself a smooth function. We can go on and on. We can just show that the d square s. Now let me write down. Now using the chain rule, I have d2s by dt square. Now remember that s is I can think of u dot and v dot as my parameters. So what is ds by dt? ds by dt is, we write it as f of u dot v dot. Now remember that f is a function here of u dot v dot, and u dot is a function of t and v dot is a function of t. So by chain rule that we have done in earlier semesters, its derivative, yani d2s by dt square, would be del f by del u dot into du dot by dt plus del f by del v dot into dv dot by dt. So that would be del f by del u dot into u double dot plus del f by del v dot into v double dot. Now these are continuous, they do exist because the function is differentiable. U dot v dot both are different, but they do exist. As I said that we usually require the existence and continuity of the second order derivative in the case of differential geometry. So u double dot v double dot exists and these are continuous. So this expression as a whole is a continuous function. So therefore we can go on and on. As long as u dot v dot is not equal to 0, we can just keep on differentiating. That means if the function is regular, that means u dot v dot is not or not both 0, right? The arc length can be differentiated as many times as we want. So arc length is indeed a smooth function if the curve is a regular curve. Now the theorem. What was the theorem? Every parametrized curve has a unit speed reparametrization if and only if it is regular. This is our theorem. Okay, again I would like to emphasize that this lecture cannot actually be a substitute of a class lecture, so you yourself have to work harder, look at the notes, look at the study material, and of course these lectures would be coming and this will augment your understanding of your course. Okay, so let's prove the theorem that every parameterized curve is regular if and only every a curve will have a unit speed reparameterization if and only if it is regular. This is our statement. So let's do the proof. Let me save some paper also. Okay, suppose that a parameterized curve is regular. Let me, okay. Okay, suppose that a parameterized curve, let me write it down, alpha from an interval AB to Rn has a unit speed reparameterization, has a unit speed reparameterization, unit speed reparameterization, and of course let us call it as we did earlier alpha tilde. Tilde, just to note, it's a reparameterization. With a reparameterization map that we have discussed earlier, phi. Reparameterization map, every reparameterization would come from a reparameterization map. Some reparameterization map which would be a bijection that would be continuous and its inverse would also be equal to continuous. So letting t then equal to phi of t tilde, as we have discussed, then alpha tilde at t tilde would be the same thing as alpha t because it's a reparameterization. So the curves that ultimately we generate would be the same, right? Alpha t would be equal to alpha tilde at t tilde for some t tilde and vice versa. So using our chain rule, if we differentiate with respect to t tilde, I would get d alpha tilde by t tilde is equal to d alpha by dt into dt by dt tilde. Different parameter. It's just a notation. You need not worry. So it would imply that norm of d alpha tilde by dt tilde is equal to norm of d alpha by dt and dt by dt tilde. Of course, it's modulus. So what does that mean? Now look at this. We showed that we are given that alpha d tilde is a unit speed reparameterization. Therefore, this is equal to 1. The velocity of alpha tilde is equal to 1. 1 is equal to d alpha by dt, right? And this is d. T is equal to phi t tilde. So this is basically d phi by d tilde in mod. Yeah, mod because it's number, this is a vector. Now since this is equal to 1, surely this can, and this is not equal to 0. Why? Now d phi by dt cannot be 0 because the function is invertible. An invertible function cannot have a derivative 0 because if its derivative is 0, then it is constant within a neighborhood of that point. If the derivative of a function, a scalar function, phi is a scalar function, if derivative of a scalar function, a function from r to r is 0 at some point, then it cannot be invertible because it would be constant within the neighborhood of that point. Therefore, this cannot be 0. Now, if this cannot be 0 and this is equal to 1, then this cannot be, obviously this is 1, the right hand side cannot be 0 in any case, right? You cannot have any multiple of 0 cannot be equal to 1. So that would mean that, what does that mean? Okay, it has therefore alpha must be regular. This alpha dot, it would mean that d alpha by dt, which is equal to norm of alpha dot t. This cannot be equal to 0. Therefore, if the curve has a unit speed reparameterization, it has to be regular. Now conversely, suppose that it is regular, then we have to show that it has some unit speed reparameterization. That means we can change the parameter, and under the new parameterization, the velocity vector would be equal to 1. The magnitude of the velocity vector of the curve would be equal to 1. Now conversely, again I stress that you go through your notes. Conversely, suppose that d alpha by dt is never 0. That means the curve is regular. It would imply that ds by dt, which is equal to norm of d alpha by dt, this would be positive for all t, because it is magnitude of a vector. This can never be negative. Plus more, this is never 0, therefore the magnitude of a 0 vector can never be 0. It cannot be 0, it cannot be negative. That means it must be positive, right? Of course, S is the arc length starting from a suitable point. Now we know that S is a smooth function by lemma's second, smooth function of t. And we have done something in calculus of first semester, from which it would follow that what we call the inverse function theorem would say that, now by inverse function theorem, that we have done, I think, of multivariate calculus would imply that S has a mapping from AB to R, because it is defined on the same interval as our curve, and it's a number. It's injective. It has to be 1 to 1 because its derivative is positive. It comes from what we call the inverse function theorem. And its image, because it is smooth and therefore continuous, would be some open interval. Is some open interval. Let me call it A tilde, B tilde. Obviously, a continuous map would always map an interval to an interval. That again you have done in your 11th, 12th class, I think. So therefore, its inverse function. Therefore, S inverse would be a map from A tilde, B tilde to AB. It's injective, therefore 1 to 1. So the inverse would be a map on its range to its domain. Its range is A tilde, B tilde, which is again an interval, and it would be mapped to AB. And again, it is from the inverse function theorem, which says that not only that inverse would exist, it would be 1 to 1. In fact, its inverse would also be smooth. This S inverse is also smooth because S is smooth. Okay, so let us define, let us use the letter phi to denote the S inverse map. Okay, so we had a curve that was regular, and from using the fact that S the arc length as a function is a smooth function, so we showed that then this S inverse, we call this S inverse our phi, and we want to get a reparameterization of this curve, which is unit speed, and we want to reparameterize in a way so that the length of the velocity vector is 1 for all values of the parameter. Okay, so I take my phi to be the inverse function, which is differentiable, and of course injective also, because S is injective, and let alpha tilde be the corresponding reparameterization let us define the reparameterization of alpha, and we will show that it would be unit speed of alpha. We use the reparameterization phi, reparameterization map phi. Okay, so that alpha tilde, at S would be alpha at t. Then if we differentiate with respect to t both sides, so we would get, using the chain rule, d alpha tilde divided by ds into ds by dt, because s is a function of t, would be equal to d alpha by dt. And taking the norm on both sides, you will get d alpha tilde by ds into ds by dt, and modulus would be d alpha by dt. But d alpha by dt is the same thing as ds by dt, and since it is positive, we can put a mod around it without changing anything. So what does that mean? It just cancels out and you get d alpha tilde by ds in norm is equal to 1 for all parameter values s. In this case, our parameter becomes s, which means that if we choose our parameter to be arc length, and we can do that only when the curve is regular, and if we do that, then this new reparameterization alpha tilde would be a unit speed curve. That's what was to be shown. Okay, now we could have thought of it earlier also. Suppose the definition of the arc length is s at t is equal to, no, s, let me write it. S is defined as t naught to t, right? Alpha at u du, alpha dot. Okay? Now, suppose my parameter, instead of t, I choose to be arc length. And arc length is a good parameter, because if when I move along a curve from a fixed point, as I move it, it clearly depends upon its arc length from t naught. So it depends upon arc length s. So we can choose that to be parameter, and when we choose that to be our parameter, our curve would automatically become a unit speed curve. But we could have thought of it here also. Suppose my parameter is s, then this would become s is equal to t naught to s, some s naught to s, norm of alpha dash at u and du. And if we differentiate it both sides with respect to s, the fundamental theorem of calculus would have given us alpha dot at s is equal to 1 for all s. Yani it would be a unit speed parameter, unit speed curve, if we choose our parameter to be the arc length of the curve itself. Now that provides, the curve is giving us everything. The parameter is also provided by the curve itself, which would define that curve. Now that makes it interesting and very helpful. Okay, I have to say something else. Okay, now that means every regular curve has a unit speed reparameterization, and that is nothing but the arc length of that curve. Arc length would always be a unit speed parameterization. So we usually denote, now since we had alpha at t our curve, and we defined d alpha by dt by this alpha dot, right? Now that this is our notation. Similarly, there is another convention. Once we write our curve as a function of arc length as its parameter, then when we differentiate it with respect to s, because this is now a distinguished parameter, it is of unit speed, so we denote it by alpha dash at s. So whenever I differentiate our curve with a parameter that is arc length, it would be denoted by dash, and whenever we differentiate it with respect to any other parameter, we denote it by alpha dot. Now dot would be differentiation with respect to any parameter, and dash would represent the differentiation with respect to the arc lengths. So this was one of the theorems that we proved, and then there is a corollary which is very easy. You can do it from the study material, which is, it's rather straightforward. Okay, in the next lecture we can come to the important point, what we call the curvature of a curve. Now that would be our starting point. These were just preliminary definitions, and the last we also did an important theorem. So that's where I would end this lecture. So let's stop it.